How about going deep, deep into the past? To the times before humans existed, before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet, even before the sun ignited or galaxies appeared in the darkness of the cosmos. So, before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding. But there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the nascent universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material, compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains. And then you try to figure out the answer to the following question. How big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now, we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique. There might be other bubbles out there, and all these bubbles move around, collide, sprout, or bud baby bubbles. In short, live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumbled down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this second universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or if our world is just a bubble among trillions of other bubbles? What if it bursts one day?
If you somehow fell into a black hole, it might change your future and erase your past. Well, at least theoretically. Let's start with the real world we live in. Here on planet Earth, your past can definitely define your future. But imagine you're not on Earth, but somewhere out there in the endless universe, and you stumble upon a certain type of black hole. The one that a UC Berkeley mathematician found. Not to mix it with a regular black hole. Let's call this type, what about a benign black hole, huh? So here's why you need a specific black hole. Thing is, you're highly unlikely to stay alive in a regular black hole. But according to some calculations made by a postdoctoral fellow, Hinz, from UC Berkeley, this specific type of black holes we agreed to call benign ones might expand at an accelerating rate. This is what makes it possible to survive the transition from our deterministic world to a black hole, which is not deterministic. Let's imagine you survived that passage, and now you're moving towards the center of a benign black hole. It's impossible to picture what's inside, and if you, as a traveler, could actually get into a black hole, you'd never be able to communicate to the outer world what interesting things are hidden in it. But it's not what interests us for now. We need to know how to get rid of the past. Hence, the mathematician you already know studies non-rotating black holes that have an electric charge. The most important thing about them is that besides the event horizon, they also have the Cauchy horizon. And here's the point. The Cauchy horizon is the place where so-called determinism simply breaks down. This may sound too scientific, but let me explain it to you. The Cauchy horizon is the place where your past doesn't determine your future any longer. So, here's a mathematically proven and apparently working method of how to get rid of your past. All you need to do is get into space, find a specific black hole, make it to the center, and get to the Cauchy horizon. However, if it sounds too complicated, you can simply try not to make mistakes here on Earth. Yeah, ideas like your past gets cancelled, you have an infinite amount of options of how your future will evolve, and all that jazz sounds as unrealistic as they are appealing. Like, imagine no one knows you failed to get into college and get a degree, but from now on, you have every opportunity to do whatever you want. But only theoretically. In reality, once you get into the black hole, not that specific one we've already talked about, you're most likely to disappear once and for all. But hey, don't be sad. I'm only talking about your current physical form. It's a bit deeper than it might seem. Thing is, there's a curious principle of quantum mechanics that can be explained in a simple way. For starters, imagine that you're not a human being, but just information. You have your experience, your background, and your thoughts. All of these are the information you are. Now, let's make it even simpler. Imagine a USB drive or a book. Both of these things contain information. If you smash a USB drive that contains music and movies, it won't exist anymore in its physical form, but the information it had will never stop existing. Same with the book. If you burn it, the information it has doesn't get burned. It continues to exist, but in another form. So, this fun theory claims that even though someone passes the horizon of events, which is a point of no return before you get spaghettified, they don't stop existing. In simple words, these universe travelers still exist, but in the form of information. Now let's go back to the black holes. According to Stephen Hawking, black holes emit radiation. Radiation makes them shrink, and with time, I mean much time, a black hole can shrink so much that it eventually disappears. So what happens to the astronaut who got entangled in a black hole if it disappears? Nope, they won't be ejected from the black hole in the way they used to exist. However, they will still be ejected from there, but in the form of Hawking radiation. But it's just a theory. Right, you remember that no one knows exactly what happens in the black hole? Another theory says that what happens in the black hole doesn't really stay in the black hole. Sounds like a good alternative to Las Vegas if all the flights for the weekends have been booked. Some scientists believe that a black hole might have a portal where you can turn back time. According to this theory, there's a white hole at the end of a black hole. If you get there, you can undo things. Like, you broke your mom's favorite vase? Hop into the white hole and it'll be as good as new there. You cooked a scramble and made a fresh orange juice, but somehow lost your appetite. It's not a problem if you cook it inside a white hole. Voila! The eggs are unbroken. The oranges are uncut and juicy again. No more food waste. Alright, turning back time sounds really cool, so I guess we might actually need a black hole to help us out. If a black hole was made in a, let's say, lab, it could devour things until it grew big enough to consume the entire planet. First, it would munch on the Large Hadron Collider, which might possibly create something similar to a black hole here on Earth. Next, Geneva, where the Large Hadron Collider is located. Then the whole country of Switzerland, then Europe. At that point, it wouldn't be long before the Earth was gone too. Luckily, if a black hole did appear, it would be so small that it wouldn't be able to do anything. Black holes actually produce a lot of energy and release it, often as heat, like a furnace. That means they will fade away when they run out of fuel. Even if a stable microscopic black hole was created, it would grow so slowly that nothing would happen. Assuming that it survived long enough to absorb the tiny particles around it, a black hole of this size would take super long to get even a pound of weight. I won't be around then. But a black hole on Earth could be a great thing. Even a relatively small one may emit enough energy to completely power humanity. We're talking a lot about food, huh? Let's not forget about spaghettification. The concept is quite simple, by the way. It's all about gravity. Imagine you're playing with chewing gum. With your force, you could easily stretch it so instead of a regular piece, you can get a long and thin one. The same happens to you. Black hole force is enough to stretch you as if you were a piece of chewing gum. Gravity holds you tight on one side, which makes you stretch. You may wonder, how come you don't get spaghettified on Earth if there's gravity too? Easy peasy. It's just too weak to do that with you. If you asked a butterfly to stretch the gum, would it be able to do that? Not likely. Their tiny limbs are just too weak. Same here. The Earth is just too weak compared to a black hole. So if you were wondering whether you'll ever reach 6'6", it may never happen on Earth. But once you're in a black hole, you can go far beyond those mere 6'6 inches. Your best height moment won't last long though. If you stretch the chewing gum at one moment, it will simply tear apart. The same will happen to you because of spaghettification. A black hole is an eerie place where those laws of physics we studied at school stop working. If a massive star runs out of its fuel, it sometimes becomes super dense and buckles under its own weight, collapsing inward and bringing space-time along. As a result, the gravitational field of this new object gets so strong that nothing can escape it, not even light. That's how a black hole is born. The black holes closest to our planet are called Gaia BH1 and Gaia BH2. They were discovered thanks to the data collected by the European Space Agency's Gaia spacecraft, hence their names. Both are about 9 to 10 times more massive than our Sun and are located a mere 1,560 and 3,800 light-years away, respectively. In cosmic terms, they're situated in Earth's backyard. And there's something seriously wrong about these black holes. So, should you pack your emergency bag? Let's find out. The remarkably close black holes are likely to represent a previously unknown category of these mysterious objects. What sets them apart from others is that they're orbited by stars at much greater distances than scientists have observed previously in other black hole companion star pairings. Normal black hole companion star systems are known as X-ray binaries. They are usually bright in radio and high-energy X-ray emissions. They swallow matter and emit powerful bursts of energy, which makes them pretty easy to spot. Now, why did it take astronomers so long to spot these massive black holes residing right inside our home Milky Way galaxy? All because they're almost invisible. In the past, astronomers spotted black holes by looking for the remnants of their meals. The thing is that when a star or even a cloud of interstellar gas is pulled into a black hole, it leaves behind a trail of electromagnetic radiation. And scientists use it to detect the presence of a black hole. But unlike other holes discovered before, Gaia BH1 and BH2 are pitch black. They don't seem to be snacking on anything at the moment. This makes them inactive, or dormant. So astronomers had to use another method. They tracked the movement of two companion stars orbiting these cosmic monsters. The stars, similar to our Sun, wobbled a bit while traveling through space. To researchers, it was a sign that something with a lot of gravity, like another star, was tugging on them. Interestingly, when they examined the area with the help of telescopes, they didn't find anything emitting radiation. So the whole situation only made sense if there was a black hole involved in the process. Luckily, Gaia is perfect for spotting invisible black holes. Thanks to its state-of-the-art equipment, it can accurately measure the motion and position of billions of stars. No other instrument is capable of such precision. Gaia's observations were backed up by the data received later by other observatories. For instance, NASA's Chandra X-ray Observatory, as well as the South African Meerkat radio telescope, revealed no visible light coming from Gaia BH2. So even though they detected nothing, it was still valuable information. It told astronomers a lot about the environment around the black hole. A lot of particles are coming towards it from the companion star in the form of stellar wind. But the researchers didn't spot any radio light. It means that the black hole doesn't have much of an appetite, and not many particles cross its event horizon, or the point of no return. Unfortunately, it's still unclear why that is. Anyway, should we be worried about those mysterious black holes lurking in the darkness of space so close to our planet? I've got some good news. There's absolutely no reason to worry. First of all, these black holes are sleeping at the moment, and it doesn't look like they're going to wake up anytime soon. Secondly, they're still too far away to affect our life, and it's not like black holes know how to travel.
Brace yourself. You're about to hear one of the most unusual sounds ever. It's come from space, and it's the sound of two black holes colliding. But first things first, our ears are designed in a special way, which helps us translate sound waves. But these sound waves become mute once the medium they're traveling through comes to an end. It happens when, for example, the atmosphere of Earth gives way to the vastness and emptiness of the cosmos. At the same time, there are some sound waves that can move even through a vacuum. And we can translate these vacuum-friendly waves into sounds our human ears can hear. That's kind of like radio transmissions work. Over the past few decades, people have sent quite many satellites to the far reaches of the solar system and even beyond. These spacecraft are equipped with sensors designed to hear such things as radio and plasma waves flowing freely through interplanetary space. These instruments are crucial for research and communication reasons. An additional bonus is that now we can finally hear different kinds of space waves as audible sounds. The results are often ear-splitting sounds, and sometimes audios are downright scary. Usually, when two black holes collide, they don't produce a sound. And still, thanks to modern technologies, we can now listen to this terrifying cosmic event. Do you hear it? This chirping sound is the sound that two black holes produced while slamming into each other around 1 billion light-years away from our planet. Interestingly, the tone of the sound rises when the holes spiral closer to each other and stops abruptly when they eventually merge. Now, do you hear that long, low buildup? It means that the merger is quite slow, more sedate, and the black holes taking part in this event are relatively lightweight. A more abrupt chirp is a sign of a fast merger, where the black holes are rather large. For example, the pair that produced this sound combined and created one black hole more than 80 times the mass of the Sun. Since each of these black holes weighed as much as several stars, they were hefty enough to produce waves while passing through space. I mean gravitational waves. They are undulations in the fabric of space-time, fanning outward at the speed of light. You can probably compare them to the ripples that appear on the surface of a pond after you throw a rock in the water. Naturally, the sound of black holes colliding isn't the only unusual noise recorded by our equipment. NASA's Juno probe passes by Jupiter every few weeks at a speed of up to 130 miles per hour and plows through all kinds of invisible fields in the process. And one of the most powerful signals it has recorded is Jupiter's bow shock. That's the point where the planet's magnetic field pushes against the incoming wind of solar particles. The sound produced during this standoff sounds similar to a sonic boom. Or this sound. It was produced by the Stardust space probe when it was passing through the dust left by Comet Tempel 1. In the process, debris hit the body of the spacecraft. It sounded as if some creature was rapping at the window or hurrying across a hard floor. Let's have a look at NASA's nuclear-powered Cassini spaceship. It spent 13 years exploring gas giant Saturn and its numerous potentially habitable moons. This mysterious and a bit spooky sound is actually radio waves emitted by the massive planet. Such waves are caused by a phenomenon which is similar to the one producing auroras on Earth. Speaking of our own planet, it's surrounded by plasma. It consists of hot, ionized particles generated by sunlight. They're constantly slamming into Earth's atmosphere. NASA's Polar mission, which was launched a few decades ago, managed to record this breath-like hiss. That's what plasma orbiting our planet sounds like. As for these weird sounds, NASA doesn't say which space probe recorded them, but they're coming from Jupiter's largest moon, Ganymede. It could have been the Galileo spacecraft, which orbited the system for around 8 years. But it probably doesn't matter so much. Just listen to this creepy noise that sounds like screams trying to break through from some hidden place.
Black holes are terrifyingly dense space objects, pulling inside everything that comes too close. Nothing can escape their clutches, even a beam of light. At the same time, black holes are some of the most mysterious objects in the universe. According to their mass, black holes are usually divided into 3 categories. Stellar black holes have a mass from a few to hundreds of times the mass of the Sun. Intermediate black holes should range from 100 to hundreds of thousands of times the Sun's mass. Scientists are now actively hunting these missing link black mysteries. But the real behemoths of the cosmos are supermassive black holes. They have hundreds of thousands to billions of times the mass of our Sun. Most supermassive black holes lie in the centers of their home galaxies. You can probably say that they sit in the gravitational driving seat. Meanwhile, hundreds of billions of stars, planets, and moons orbit them. Let's have a look at the biggest black holes astronomers have found so far. NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's actually an elliptical galaxy that has an active nucleus in the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers 2 symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving toward us. The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. This S5 Theora 1481 is one of the most interesting black holes on our list. It has a mass of 40 billion solar masses and is actually a blazar, the most energetic of all quasars, which are super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of IC 1101, it has a mass of 40 to 100 billion solar masses and emits clear radio signals. Recently, astronomers have discovered a gravitational space wonder that is swollen to really unimaginable proportions. The black hole I'm talking about is Ton 618, and it's a mind-boggling 66 billion solar masses. The thing is so massive that astronomers had to think of a new term to describe it. They came up with an ultramassive black hole. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole, and it still won't be enough to create a Ton 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You probably know that black holes are made of matter packed together as densely as possible. And still, it doesn't mean that black holes are some kind of space predator, roaming galaxies and munching on everything they come across. Ton 618 still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. What I want to say is that the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try to do it and you'll see. What if the sun, our precious source of light and heat, got swallowed by a black hole? Or even more worrying, what if such a black hole was brewing inside our star right now? Would the sun eventually collapse in on itself, pulling along everything in the solar system? Well, if a medium-sized stellar black hole, formed by the gravitational collapse of a star, swallowed the sun, we would only have around 8 minutes before things went haywire. But if our star swallowed a tiny primordial black hole, we could probably have a chance to survive. The existence of primordial black holes hasn't been confirmed yet. These hypothetical black holes are believed to have formed right after the universe was born. Unlike supermassive or even stellar mass black holes, primordial ones are typically tiny. Their mass is roughly the same as the mass of an asteroid, and their size is no larger than that of a baseball. You can find primordial black holes in a few theoretical models, which have been used in attempts to explain loads of mysterious space stuff, from hypothetical Planet X to dark matter. There's actually a theory that primordial black holes could actually be dark matter. If primordial black holes indeed existed, they could appear because some regions of space were hotter, others were cooler, and some areas were extremely dense. Scientists believe these dense spots could collapse into primordial black holes. The most curious thing, though? These holes might be so small exactly because they popped up right after the Big Bang. The thing is, the longer it took a black hole to appear, the larger it was. The mass difference between older, smaller, and younger, bigger black holes was incredible. Compare the mass 1,000 times greater than our sun's and that of a pea. There you go. By now, the smallest primordial black holes have most likely evaporated away, but some bigger ones can still be scattered out there in space. Many theoretical models claim that primordial black holes are so common that it's kinda inevitable for a random star to capture one. Such stars with black holes at their centers are known as Hawking stars. So, what might happen after such an accidental acquisition? At first, a captured primordial black hole isn't likely to have any effect on a sun-like star. After all, compared to our massive star, an asteroid's worth of mass might as well be a speck of dust. The black hole simply isn't able to consume much of the sun, but with time, its persistent presence in the heart of the star can start affecting things. The black hole is likely to begin consuming matter in the stellar core, growing over time. If this process is fast enough on a cosmological scale, the black hole can end up swallowing the star completely. If the process is too slow, it might still influence the development and lifespan of the star. Mostly, it depends on the initial size of the primordial black hole. A large one with around 1/1000th of the solar mass can potentially consume a star in less than 500 million years. If something like that has ever happened, there must be solar mass black holes out there, too small to have been created by supernovae like regular stellar black holes. If the primordial black hole is way smaller, a trillionth of the solar mass, things might get complicated. This tiny hole will keep munching on the star's core, but at a very slow pace. And still, it will stir things up in the core of the star, making it heat up more than usual. Eventually, the host star will swell into something cooler and redder than usual red giant stars. Plus, the turbulence at its core is likely to affect the surface activity of the star. Since we haven't observed anything like this happening to our sun, it's very unlikely that there's a primordial black hole at its center. But we can't say for sure that there aren't other stars hurtling through space, carrying primordial black holes in their hearts.
Black holes are some of the most enigmatic and sinister phenomenon in the universe. They can swallow up entire stars and planets, bending the very fabric of space and time. But what if Earth, our home planet, were to be caught in the grip of a black hole's event horizon? What would we see before the inevitable end? Well, let's have a look-see, okie dokie. So a black hole is like the bully on the playground. You avoid them at all costs. It's a region of space where gravity is so strong that nothing, not even light, can escape it. It's like Houdini in reverse. As with snowflakes, every black hole is unique. Each one has its own mass, spin, and charge. And they also come in different sizes, sort of like jeans. Petite, slim, regular, and husky, or something. Anyway, there are 4 sizes. The smallest black holes are the stellar mass kind. They're born when the massive star runs out of juice and folds in on itself. They're like the chihuahuas of the black hole world. They may be tiny, but they're feisty. They gobble up nearby matter like a hungry puppy. And even the smallest one is 3 times more massive than our sun. Next up, we have the middle children of this cosmic family, intermediate mass black holes. They're too big to be born out of collapsed stars. Scientists believe that they may be created when several black holes merge into one. And even though they can't dominate galaxies, at least they can swallow up some nearby stars. Goody for them, huh? But do you know who can dominate a galaxy? The enormous monsters of our universe, supermassive black holes. They're the giants with masses ranging from millions to billions of times that of our sun. And they play a crucial role in the growth and formation of their host galaxies. Finally, there are ultra-massive black holes. Trust me, you can't even imagine the size and mass of these guys. These cosmic eldritch horrors are extremely rare, but the ones we know can devour entire galaxies like Pac-Man. So, what happens if you get too close to a black hole? Or more like, what would you see in your last moments? Well, first, you reach an event horizon. It's like a point of no return, an invisible boundary that marks the edge of a black hole. And here's where things start to get really weird. For example, time starts to slow down. Not for you, for an outsider watching you from a safe distance. If you were falling into a black hole, you wouldn't feel any different. But if you were watching someone else fall into it, you'd see them slow down and eventually freeze in time, like in a paused video. As you get even closer, you would start to see some pretty mind-bending things. The gravity would cause the light around you to bend and distort, creating a sort of funhouse mirror effect. You might even see a halo of light around the black hole, known as the photon ring, or jets of high-energy particles spewing out from the black hole's poles. You can actually get pretty close to a black hole without feeling any major effects. It's only when you cross the event horizon that there's no going back. Your goose is cooked. After crossing this boundary, you'd be unable to see anything. For the person watching you from the outside, it would be as if you had suddenly disappeared. Meanwhile, you might start feeling a bit stretched out, like a piece of spaghetti. This is because the gravity is so stark that it's pulling you in different directions at once. There's even a scientific term for it called spaghettification. We'll cover linguinification in another video. Now that you're inside a black hole, you're taking aim at the singularity. It's a point of infinite density in its center, where all matter is crushed down to a single point. It's like trying to fit an elephant into a tiny matchbox. Everything gets squished together until it's as small as it can possibly be. Which means it's time to wave goodbye, I guess. And if all that sounds scary, here's another fun fact. Black holes are not rare at all. Actually, there's one in the center of each galaxy, including our own Milky Way. So, does it mean that we'll eventually be sucked into it? And if so, how exactly would it happen? Well, let's see. Imagine a black hole approaching our solar system. At first, it appears as nothing more than a tiny speck in the distance. But as it gets closer and closer, its gravitational pull begins to wreak havoc around. Planets start to veer off course, asteroids are flung into oblivion, and comets are shattered into a million pieces. But just like waiting for the sausage to be served in a German restaurant, the worst is yet to come. Yeah, like that joke. Soon, it inevitably reaches the Earth. First, our planet's atmosphere would be pulled toward the black hole, triggering a massive windstorm. And there'd be huge waves on the oceans, the water itself being distorted by gravitational forces. Imagine seeing seas and oceans getting stretched out. Earth's magnetic field is generated by the motion of molten iron in the planet's core. But now, the extreme tidal forces of the black hole would disrupt this motion, causing the magnetic field to weaken and distort. All this would cause massive earthquakes and volcanic eruptions as the planet's crust and mantle were pulled apart. All infrastructure and technology would be completely destroyed. Buildings, bridges, and roads would be torn apart. Okay, let's hit the pause button. Pretty horrifying, isn't it? Nah, but don't worry. You wouldn't have even seen that much, because you would have felt the effects of the black hole much, much earlier. Well, back to the future. We'll lose our magnetic field even before everything started to collapse. And this means not only that the weather and climate will become terrible, we'll also be exposed to extreme radiation. These gamma rays and the heat from the black hole could drastically change our planet. Say ta-ta to all our beautiful nature. At least misery loves company. We won't be the only ones affected by a black hole, which is probably even worse. As this beast engulfed the entire solar system, it would consume about everything. One immediate effect would be the disruption of the orbits of asteroids, comets, and all the other bodies. The planets would begin to deform and stretch, their surfaces warping like molten metal. The sun itself would be affected, its surface contorting like a glob of putty. And yeah, all this is scary even to imagine. But now, breathe and relax, because none of this will ever happen. This is the bright side, remember? Your infinitesimal odds of winning the big lottery are even better than the Earth ever being swept into a black hole. The nearest black hole to our solar system is called Gaia BH1. Discovered by scientists in 2022, it's found in our own Milky Way galaxy, about 1,600 light-years away from Earth. Gaia BH1 is about 10 times the mass of our Sun, which makes it a stellar mass black hole. It's not very interesting on its own, but its discovery has supplied valuable insights into the behavior of these cosmic monsters. But as you can see, even the closest known black hole is over 1,000 light-years away. They move very slowly, and they'll never get so close to our system to pose some kind of a threat. Hey, but didn't you say there's a black hole in the center of the Milky Way galaxy? Doesn't that mean it's going to eventually hoover up our entire galaxy, you may ask? Maybe not in that voice. Well, don't worry. The correct answer is no. The one in the center of our galaxy is called Sagittarius A star. You may remember it from that viral blurry photo that circled around the internet a few years ago. This black hole is indeed very massive and has a strong gravitational pull, like two 8th graders in love. However, it's still a small beam. It only affects objects that are close to it. The objects in the galaxy are all too big and move too fast to be pulled in by black holes. Nevertheless, they're still fascinating objects to study. Scientists are still trying to unlock the mysteries of black holes. And even though they'll never be dangerous to us, they're still a huge reminder of the incredible power of our universe. Now I think I'll turn my attention to the incredible power of chocolate. Now really, an object weighing billions of times the mass of our Sun must be easy to find, right? Wrong. Unfortunately, it might not be that simple, like in the case with a missing black hole. But let's travel to the galaxy cluster Abel 2261, hosting a supermassive black hole at its center. Or at least, that's where it's supposed to be. The main problem is this giant space phenomenon is nowhere to be found. Now, supermassive black holes are mega monsters, churning slowly at the center of their home galaxies. They gather tremendous clouds of gas and dust around them, which makes them swell up to sizes the human mind can't begin to imagine. If a supermassive black hole, like the one that dwells at the center of our home Milky Way galaxy, moved even a little bit closer to our solar system, we'd be doomed. The distance between this huge thing and Earth could be several dozens of light years, and still, it would wreak havoc on our planet. Earth, along with other things making up the solar system, would be tugged into the black hole's orbit and doomed to spin around it for eternity or longer. Hey, who knows, right? So, it's good that such black holes stay away from us at the moment. So, let's see what happened to that runaway supermassive black hole from that gigantic cluster of galaxies around 2.7 billion years away from our planet. Scientists have been looking for it with the help of NASA's Chandra X-ray Observatory and Hubble Space Telescope. But so far, no result. The main problem with finding a black hole is that it's, black. And space is, you guessed it, black too. So there's no contrast whatsoever that could help astronomers spot the hole. But scientists haven't given up yet. After all, they have a lot of other technologies to find black holes, small and big, in the vastness of space. Some of these methods involve watching the stars orbiting black holes. Sometimes it's a fake gravitational wave signal which is produced when two black holes collide. But the most reliable technique is watching dust and gas falling to their doom. The thing is, black holes are space objects with insane gravity. So regions of space surrounding them are usually a bit chaotic, gas and dust getting pulled into the bottomless abyss, compressing and heating up. In the process, it releases a flood of X-ray radiation. So, astronomers look for extremely bright X-ray sources in the universe. Chances are those are the last gasps of giant clumps of material before they disappear into a black hole. Then, why can't scientists find such X-ray signatures left by the black hole in Abel 2261? One of the most mysterious things about its disappearance is that radio telescopes have spotted some signs of massive plumes of superheated material launched at one point within the last 50 million years. These plumes were most likely caused by a large black hole, which is nowhere to be found these days. So, at the moment, we can only play a guessing game. Maybe two medium-sized black holes collided, pushing the newly merged giant out of the center of the galaxy. The observations of the stars in that galaxy have shown a clump of dense material a few thousand light-years away from the galaxy's core. Maybe it's the runaway black hole, but disappointingly, no X-ray signals are coming from that clump. Or the hole might still be there in its rightful place, but it's, slumbering. If it doesn't get a fresh supply of gas and dust, it has nothing to feed on. As a result, it can't release a flood of X-rays. But again, the answer, do not disturb, the black hole is sleeping now, isn't very satisfying. Why isn't it getting its space food? What happened 50 million years ago? What is that clump of material speeding away from the galaxy center? So many questions, and no answers so far. At least, we know what black holes look like. Well, kinda. It's actually the shadow of a black hole's event horizon, visible against the glowing superheated material falling inside the hole. The first ever mugshot of a black hole appeared in 2019, but the data for its creation was collected in 2017. It took an international team consisting of more than 200 astronomers 2 years to assemble the image. We can admire this amazing space phenomenon thanks to a vast global network of telescopes called the Event Horizon Telescope Collaboration, or simply EHT. Why such a name? The thing is that the event horizon is a point of no return on the outskirts of a black hole. When something, for example, matter, radiation, or light, reaches this boundary, there is no way for it to escape the black hole's clutches. Anyway, to capture that very first image of a black hole, scientists created a virtual telescope that turned out as big as our planet by combining the power of 8 powerful radio telescopes. But it wasn't an easy feat. The researchers had to simultaneously point the telescopes in a meticulously planned order with the help of precise atomic clocks set on each telescope. Plus, to keep the chances of rain and bad weather to a minimum, they even constructed the telescopes in super dry regions, such as the Atacama Desert in Chile and the South Pole. On each observation day, the telescope gathers roughly 350 terabytes of data. That's 10 times the amount of data collected every day at the Large Hadron Collider. But let's speak more about black holes themselves. There are stellar black holes, smaller but even more dangerous than their supermassive peers. They appear when stars that have run out of their star food fall into themselves. If a star used to be big enough, it keeps compressing and compressing some more, and voila! A baby stellar black hole is born. But even if I call such a hole a small one, it's still 5 to several tens of times heavier than the Sun. Unlike their massive siblings, hypothetical mini black holes could be really tiny, not bigger than an atom. Even so, just one minuscule thing would have the mass of 1,000 SUVs. One theory claims tons of micro black holes could have been created right after the Big Bang and the beginning of the universe. Some scientists even go as far as to say that a couple mini black holes pass through our planet every day. There is a supermassive black hole smack dab in the middle of our galaxy, the Milky Way. Its name is Sagittarius A star, and it's 4.3 million times as heavy as the Sun. And nope, we aren't going to be pulled into this hole. It's more than 26,000 light-years from Earth, too far to have any influence on our planet. By the way, recently, astronomers have discovered that this supermassive black hole might be leaking. If it's true, it probably means that Sagittarius A star isn't a sleeping giant, as previously thought. It might still be active. And the leakage recorded by scientists may be the hole hiccuping while swallowing clouds of gas. Maybe we should burp this baby? If you ever find yourself near a black hole, get ready that time will significantly slow down. It may work for you if you aren't eager to grow older. Just don't let yourself be tugged beyond the point of no return. Another danger of hanging around a black hole is that it might start behaving like a massive galactic volcano. From time to time, black holes flare up, but instead of spewing lava, they produce enormous amounts of energy, and it makes gaping holes in the surrounding material and gas. A short time ago, scientists discovered one of the largest craters in the universe. Radio and X-ray telescopes detected a supermassive black hole that threw a temper tantrum many years ago. It happened in a galaxy cluster about 390 million light-years away from Earth. The crater left behind, which was actually a hole punched in the cluster's hot gas, could fit 15 Milky Way galaxies. Okay, mind blown, I'm out of here.
You might think falling into a black hole is as easy as falling into a giant pit. But boy, is it a whole different ballgame. To actually fall into a black hole, you would need some incredible luck and a dash of wizardry. Moreover, if you were watching something fall into a black hole, you wouldn't even see it. Why? Well, let's try to understand the magic of physics. Falling into a black hole is really tricky. First of all, to even have a chance of doing this, you would need to aim perfectly and start your journey from very far away. It's like trying to hit a tiny target from a long distance. That's because black holes exist within galaxies, which are filled with other objects like stars, planets, and gas clouds. These objects have their own gravitational forces that can influence the path you need to take. It's like you have to carefully navigate through the room, avoiding bumping into others or getting pulled off course by their movements. In a similar way, when falling into a black hole, you need to navigate through the influences of other celestial objects. As you get closer, things get even more complicated. Making even the tiniest change in direction would require a tremendous amount of energy that you wouldn't be able to generate. It's like trying to steer a spaceship with no fuel left. This is because the black hole's gravitational pull is immensely strong. Once you pass the point called the event horizon, there's no coming back. You wouldn't be able to control anything. Now, even if you somehow manage to get on the right path and avoid all the obstacles, there's still a dangerous situation waiting for you. The intense heat and energy around the black hole, called plasma, would fry you as you get closer. So, you would need some impossibly strong protection to get even close to it. But not only is it nearly impossible to fall into a black hole, it's also impossible to see someone falling in it. Why? Let's find out. Imagine you're standing far away from a black hole, watching something getting closer and closer to the event horizon. As this thing, let's say it's a spaceship, falls into the black hole, two very strange things start happening. First, the color of the spaceship will change. You see, the gravity near a black hole is incredibly strong, much stronger than anything we experience here on Earth. This intense gravity affects everything around it, including light. Now, light has this fascinating property where it carries energy. But when light gets close to a black hole, the powerful gravitational pull starts sapping away its energy, kinda like stealing it, making light weaker. And you know how when you look at a beautiful sunset, the sun appears to be this warm, reddish-orange color? Well, that's because when sunlight travels through our atmosphere, it scatters and loses some of its higher energy bluish colors, leaving behind the redder ones. So when light loses energy, it tends to shift towards the red end of the color spectrum. The same thing happens near a black hole. The light from the spaceship loses energy due to the black hole's strong gravity. So, the spaceship, which initially had its own color, starts looking redder and redder as it gets closer to the black hole. It's as if the black hole is casting its magical spell, changing the color of the spaceship itself. The second weird thing is related to time. According to a theory of general relativity, gravity can mess around with time itself. And it works in a very strange way, because none of you, not you, not people on board a spaceship, will feel this change. For you, an observer in this scenario, time is flowing just like it always does. You're just sitting there, sipping your space lemonade and watching the spaceship's journey. For people on a spaceship, things are the same. Their watch ticks away at a regular pace, and they go about their day as usual. But, objectively, for you, it would be like watching a spaceship fall in slow motion. It will seem to you that it's been falling into a black hole for weeks or even years. You might turn 80 and the spaceship is still out there. Crazy, right? Now, if time slows down for the spaceship, it means the light it emits also slows down. So, imagine someone on that spaceship flicking a flashlight on and off. But because time is moving so slowly, the light coming from the flashlight also moves in slow motion. It takes ages for each burst of light to reach your eyes. You'll be watching a spaceship as if you're watching a video in super slow motion. And when light takes longer to reach your eyes, it becomes weaker and dimmer, just like a fading star. So, as the spaceship gets closer and closer to the black hole's event horizon, not only does it start looking redder, but it also appears dimmer. So, it becomes harder and harder to see the spaceship as it gets closer to the black hole. It slowly fades away, like a disappearing act on the grandest stage of the universe. Pretty mind-boggling, isn't it? But that's all about you, the observer. And how are people on board doing? What do you actually experience when you fall into a black hole? As you get closer to the black hole, something really weird starts happening. The gravity near the black hole is so powerful that it stretches and warps everything around it. so the difference in gravitational pull between your head and feet becomes significant. This difference creates a tidal force, which stretches your body like a long, thin shape. It's a process that's scientifically called spaghettification. Essentially, you would be stretched into a human noodle. Being turned into spaghetti might sound fun for a pasta lover, but it's definitely not so great for an astronaut. Meanwhile, colors around you begin to warp and distort, creating a dazzling light show. It's like riding a roller coaster through a rainbow tunnel. Twists and turns, flashes and sparks. It's an exhilarating, mind-bending experience. And then, what happens to you depends on the type of black hole. First, we have classical black holes. These are black holes that exist forever. If you fall into this black hole, it would take an incredibly long time to reach the center. The center would keep getting closer and closer, but you would need an almost infinite amount of time to reach it. So it would feel like your journey would never end. And then we have evaporating black holes. These black holes can evaporate over time due to a process called Hawking radiation. It's just like the ice cubes melting away. These black holes have a limited lifespan, and it's basically impossible to fall into one of them. As you approach the evaporating black hole, you find yourself hovering near its edge, the event horizon. It's like being stuck at the entrance of a super cool amusement park. But guess what? This amusement park is shrinking. The black hole is evaporating, and as it does, the event horizon gets smaller and smaller. So you stay right at the edge, tracking its every move, but you will forever stay in this event horizon without ever crossing it. But remember, once you pass the point of no return, there's no way back. You're on a one-way ticket to the mysterious heart of the black hole, the singularity. At the singularity, everything goes bonkers. Our current understanding of physics goes haywire, so it's a bit like entering a magic show. What happens once you reach the singularity? Is there anything on the other side of a black hole? We have no idea. It's a big mystery for us, but maybe we'll figure this out someday. So, my friend, it's best to admire black holes from a safe distance and let your imagination soar with the incredible wonders they hold. Just remember to keep your pasta on your plate and not near these cosmic spaghetti makers.
Somewhere, deep underground in super-secret laboratories, scientists are trying to create a black hole. It looks like the latest experiment was a success. The black hole hovers above the desk for a moment, but then, in a split second, it swallows it whole. Uh-oh. After its meal, the black hole grows until it is out of control. Microscopes and test tubes fly into the dark void. Soon everything in the room has been consumed. Each time it eats, it grows bigger and bigger and attracts even larger objects. On the surface, people go about their day as usual. Some joggers stop their run when they see a giant black sphere growing in the distance. Houses are torn from their foundations, and cars fly through the air towards the black abyss. In just a few minutes, the black hole has enveloped our entire planet. Then it grows big enough to consume the Moon and Mars. The black hole is now heavier than anything in our solar system. All of the planets begin to circle it before becoming food for the monster. Finally, even the sun is extinguished in the belly of the beast. Well, that was pretty bleak. Don't worry, this isn't how the scenario would play out in real life. Our scientists may actually be capable of creating a black hole, but it's far safer than this. The effort to make a black hole is led by the scientists working in Geneva on something called the Large Hadron Collider. This machine basically makes particles move at high speeds until they collide. When this happens, they release a lot of energy and create a lot of interesting effects. Scientists think that energy released by these collisions might be enough to create a black hole. Some people were so worried by this that they even tried to ban the construction of the Large Hadron Collider. Luckily, if a black hole did appear, it would be so small that it wouldn't be able to do anything. Black holes actually produce a lot of energy and release it, often as heat like a furnace. That means that they will fade away when they run out of fuel. If one appeared in the experiment, it would instantly burn out and disappear in a billionth of a second. Even if a stable microscopic black hole was created, it would grow so slowly that nothing would happen. Assuming that it survived long enough to absorb the tiny particles around it, a black hole of this size would take about 500 billion years to gain a pound of weight. Black holes could actually be really useful. One with the mass of Mount Everest would emit enough energy to completely power humanity. Even better, black holes are so dense that the one this big would only take up a tiny bit of space. We couldn't create anything as enormous as the naturally occurring black holes, though. Some can weigh hundreds of thousands of times as much as our Sun. Recently, scientists have observed a real black hole feast. The sight of a black hole tearing an enormous star apart is one of the most mesmerizing sights in the universe. Heavier and more destructive than anything else in existence, the black hole is both amazing and terrifying. And black holes aren't actually black at all. They're so massive that even light can't escape their pull, meaning that they're actually invisible. Scientists can only find them with special instruments. Most natural black holes are born as stars reach the end of their lifespan. You can picture healthy stars as giant furnaces that burn hydrogen and give off unbelievable amounts of energy. Every second, stars like our Sun produce more energy than humanity has ever produced, which pushes outwards and makes it want to expand. This is what eventually finds its way to Earth as the heat that birthed life on our planet. The only thing stopping this expansion is gravity, a force that basically just pulls objects toward something heavy. Most people know gravity is something that keeps us planted to the ground and stops us from flying off into space. The force of gravity of a star is so strong on stars that it makes them want to implode in on themselves. So, when a star is healthy, the force of gravity pushes inwards, and the energy it releases tries to inflate it like a balloon. These forces mostly cancel each other out and stop it from doing much at all. When a star burns through its fuel, though, nothing is pushing outwards to stop it from collapsing in on itself. Some really big stars make so much energy that they gradually expand into something called a red giant. When they run out of fuel, they cool, and gravity pushes the enormous object into a tiny space. Scientists use our Sun to measure how big things in space are. Our Sun weighs 1 solar mass. If a light star, like our Sun, implodes, not much happens, which is lucky if you've ever worried about being swallowed up into a black hole. If a red giant around 10 solar masses implodes, though, some incredible things can happen. The collapse of one of these is so intense that it explodes into a supernova, releasing a light as bright as the entire galaxy. Stars that are massive enough to produce supernovas sometimes become black holes. Their weight causes gravity to push down and compact them until they collapse into a black hole in less than a second. The inside of a black hole is mysterious and unexplored, for obvious reasons. One thing we do know is that they're so massive that they can even distort time. 1 second near the black disk can be equal to weeks or even months on Earth, depending on its size. In 2019, scientists watched a black hole devour a star the size of our Sun. Even though it was 860,000 miles wide, the star was completely trapped in the black hole's gravitational field. For a while, they danced around each other, gradually coming closer and closer. Eventually, though, the star was extinguished in the invisible mouth of the black hole. The black hole sometimes releases beams of energy into space. Sizzling plasma flies out at 6,200 miles per second as the black hole finishes destroying the star. About half of the star's mass is consumed, while the rest is ejected into space. Incredibly, these insatiable titans even consume other black holes when they get big enough. The collision of 2 black holes was recently witnessed by scientists, when one, weighing in at 85 solar masses, met another that was 66 solar masses. When black holes interact, the bigger one always swallows the smaller, adding even more mass to itself. The resulting black hole here reach 142 solar masses big. It's hard to believe, but this is still very small for a black hole. It will continue to consume everything around it and might even reach the size of a supermassive black hole at some point. These are unbelievably big and destructive. Our entire galaxy, the Milky Way, rotates around the gravitational field of one of these supermassive black holes. This monster weighs around 4 million solar masses, or more than 1 trillion times our planet, and that isn't even the biggest they get. It's also theorized that black holes can be made without a dramatic explosion. Big gas clouds that weigh hundreds of thousands of solar masses could condense under the force of their gravity to make a star. This object would already be so heavy that it would continue to compact until it became a black hole, skipping the supernova stage. Supermassive black holes are so far away and hard to observe that scientists doesn't have a full understanding of them yet. We don't know much about what happens inside a black hole, leading to a lot of speculation. For decades, people have theorized about how we could use black holes. Knowing that black holes distort time means that someone could use it to travel to the future with the right technology. If it was possible to build a ship strong enough to withstand the powerful gravitational fields, it would be simple. All they would need to do is decide how far they want to go and fly around the outside of the black hole. In the few minutes or hours they spent near the time warp, years could have passed back on Earth. They could be thousands of years old without having aged at all physically. Wow, that's officially a mind-blower. So, you're standing on a diving board in the middle of an open space. You look down, but that's not a pool. It's a giant black hole. Well, what the heck. You start swinging and then you jump. The gravity of the black hole grabs you, and you pick up speed. Just a little more, and you'll enter the dark abyss. But you're not afraid. You're sure you can survive the fall into the black hole. Besides, you have a clear goal: to travel through time. But first, let's figure out how it works and why time stops near a black hole. This is the space-time grid. It's what our entire universe is made of. And just like a regular grid, it sags if you put something heavy on it, like me. For example, let's put the planet Earth here. You see a little funnel that is formed around the Earth, and if you put a small ball next to the planet, it'll roll into the funnel. That's how gravity works. The heavier the object, the more it bends space-time. By comparison, here's the Sun. It's almost 333,000 times heavier than the Earth, so it makes a really big funnel. So big that all the planets in our solar system move around that star inside that funnel. So now, let's put a black hole on a space-time grid. Its centers are infinitely heavy, so they create a limitless deep well. And anything caught in the black hole's gravitational field can never leave it, not even moving at the speed of light. Okay, their gravity is infinitely strong, but why do they slow down time? It's all about the speed of light. According to physics law, the speed of light must be the same at every point in our universe, even in a black hole. So, for our experiment, we take this ball, a photon of light that can travel 671 million miles per hour. You could get from Earth to the Sun at that speed in 8 minutes. That's how long it takes light to travel from our star to our eyes. So, when you're looking at the Sun, you're looking back in time 8 minutes ago. By the way, don't look at it directly. Now, the critical thing to remember here is that velocity consists of two physical quantities: space, miles, and time, hours. We'll use that later. Now, let's look at the black hole in our space-time grid. In three-dimensional space, it appears like this. But if we assume that space is two-dimensional, our grid looks like this when viewed from above. Just a lot of squares. And this is the black hole right in the middle. If you look at the grid from the side, you'll see a straight line. And the black hole here looks like a pit, or like an endless well. Now, let's follow our photon of light in three-dimensional space. Here, it's moving toward the black hole, and then it falls into the well of the black hole, and it continues its motion at a constant speed. Now, the side view. Again, the photon moves from left to right and then falls. Its velocity doesn't change. The problems begin if you look at the experiment from above. When the photon of light moves in the distance of the black hole, its speed is stable. but then it goes down into the well. First, it slows down and then it just stands still. But it's moving downwards. The photon moves in an arc down the well in the lower dimension without changing its speed. But in the higher dimension, it traveled a minimal distance at the same speed. Usually, this would mean that the photon was moving at a low speed in the second case, but not in the case of the speed of light. Remember, it must be the same at every point in the universe. The number 671 million miles per hour shouldn't change. So, we change the very parameters of that number, time. Time itself must slow down so much that this slight movement of the photon, when you look at it from above, was at the same speed, 671 million miles per hour. But if you go down and look at this well much lower, you see that its walls are almost vertical. So, a photon of light would be moving in a vertical trajectory. That means that if you look at it from above, the photon will just be standing still. Again, its velocity can't change, so time will vary. At that point, it should just stop. This is what happens near a black hole. Now, if you look at a black hole, you can see this effect in action. It swallows up the light around it. But as for an observer, it seems to you that the light stays in orbit around the black disk. In fact, at that moment, the photons are still moving at the speed of light inside the black hole. It's because time has slowed down there so much that you feel like the light has stopped there. This disk is called the event horizon, the point of no return, the last stop before you go into the black abyss. And at the very center of the black hole is the singularity. This point of space is so dense that if you tried to describe it with any numbers or physical quantities, they would all tend toward infinity. Simply put, all the laws of physics we know just stop working here. So scientists can't say exactly what awaits you in the singularity. Before you make that jump into the black hole, let's drop a space probe there with a blue light that flashes once per second, and let's attach giant clocks to it. You see the probe falling into the black hole, gaining speed. But then it starts to slow down. Moreover, the probe flattens out and seems to spread out around the black hole. And then you notice that the blue beacon on the probe has changed its light. It now flashes as red. It's because the light is a wave. Blue is a truly short wave with a high frequency. But the black hole's gravity acts on this wave, stretching it out. The light waves get lengthened and become broader and less frequent. The new wavelength and frequency match with the red color. It's called redshift. Also, the probe blinks now not once a second in short beeps, but lights up and goes out for a long time. It's because of the time warp. If you, as an observer, look at the clock on the probe, the second hand there barely moves. However, the clock on your hand works as usual. But if you could be in a black hole, time would seem normal to you, and the arrow on the clock would move as it did before. But the hands on the clock outside the black hole would move like crazy to you. That's because time goes much faster outside the black hole. Oops, your probe just got ripped apart. That's because of the substantial difference in gravity that acts on the probe. The black hole's gravitational force increases with every foot of approach. That is, if you were to extend your hand toward the black hole hard, the gravity on your fingers would be much stronger than on your shoulder. This force would cause your fingers to lengthen, simply like spaghetti. That's why many people think it's impossible to survive falling into a black hole. But scientists think you could survive without a problem. Hey, maybe they should jump first just to make sure. The thing is, you have to pick a black hole as big as possible, like the ones at the centers of galaxies, for example. That bright spot at the center of the Milky Way also has a black hole. It's about 1 million times heavier than the Sun. And this is the Messier 87 galaxy, one of the most massive galaxies among our neighbors. In 2019, humanity got its first ever photo of the black hole at the center of this galaxy. It's about 6.5 billion times heavier than our Sun. So, it's the perfect place to make your jump into a black hole finally. Let's go. At first, you feel a strong acceleration as the incredible force of gravity grabs you. But in the case of a supermassive black hole like this, the gravity doesn't change as dramatically. That's because of its size. Right now, the gravitational force on your legs is about equal to the gravitational force on your head, so you don't turn into spaghetti, and you feel comfortable. You see that the light from the stars and all the space around you has begun to shrink at a certain point. It means that you have already passed the event horizon and are now moving toward the black hole's heart. As a result, the light of the universe becomes a small dot for you and then disappears altogether. If we look at our space-time grid, you're already falling into a well. Time is completely stopped for you. However, the rest of the world continues to move steadily through time. If you could now look at the Earth from a black hole, you would see a time lapse, an accelerated video of how the months and years go by on our planet. If you had a jetpack that had an incredible engine to pull you out of the black hole, then you can make a jump forward in time. In 1 second, centuries on Earth could pass in the heart of a supermassive black hole. But this only works one way. You can't go back in time. But for now, you keep falling into the black hole. Beyond that, no one knows what'll happen to you. We only have theories about wormholes and white holes that might transfer you somewhere else in the universe. So, enjoy your trip, and just think about all the frequent flyer miles you're racking up. Despite how much we already know about black holes, there are things that are still a mystery. For example, these space monsters seem to gain weight even when there's nothing for them to feed on. This realization might shed light on mysterious dark energy, but I'll talk about that a bit later. Most supermassive black holes lie in the centers of their home galaxies. You can probably say that they sit in the gravitational driver's seat. Meanwhile, hundreds of billions of stars, planets, and moons orbit them. Even though black holes are really, really big, physics makes it almost impossible for them to grow. But we've found one of these space wonders that has swollen to really unimaginable proportions. The black hole I'm talking about is Ton 618, and it's a mind-boggling 66 billion solar masses. The thing is so massive that astronomers had to think of a new term to describe it. They came up with an ultramassive black hole. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole. And it still won't be enough to create a Ton 618. So the question is, how did this ultramassive black hole turn into such a behemoth? You probably know that black holes are made of matter packed together as densely as possible, to the point where gravity gets so powerful that not even light can escape it. And still, it doesn't mean that black holes are some kind of space predator, roaming galaxies and munching on everything they come across. Ton 618 still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. What I want to say is that the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try to do it and you'll see. First of all, the material needs to get close enough to be affected by the black hole's gravity. And that's not so easy, considering how vast the universe is and how relatively small in size black holes are. But if something does get close enough, there's no escape. That's true. The force of gravity around the black hole increases dramatically fast. It even creates the effect of spaghettification, when an object gets stretched into thin strands of space pasta due to the influence of gravity. Once spaghettified, the matter then gets pulled into the black hole's orbit and flattened into a swirling and glowing disk of material. Eventually, this matter settles into a nice orbit around the black hole, quite far away from the point of no return, also known as the event horizon. By the way, we can use the event horizon to estimate the size of a black hole. The larger it is, the more massive the black hole you've come across is. Interestingly, getting the matter to cross the event horizon will be the most difficult part if you decide to grow yourself a black hole. You'll need to push the material out of its stable orbit around the black hole and make it fall in. As an example, we can take the Sun and Earth. Despite the star's enormous gravity, our planet doesn't get pulled toward it. And the main reason why the material can cross the event horizon is collision between particles. This way, they gain some energy, which is enough to send them spiraling into the black hole. But what happens afterward? The center of the black hole likely collapses into something called a singularity. That's infinitely dense material crammed into an infinitely tiny point in space. But the main problem here is that singularities are mathematically impossible. That's why some scientists suggest that when this weird stuff happens inside the black hole, its mass gets linked to the expansion of the entire universe. Yep, when it gets weird in space, it gets really weird. Such a coupled black hole is like a rubber band being stretched along with the universe as it expands. And as it stretches, its energy increases. And since mass and energy are proportional, the mass of the black hole increases too. But this new mass creates a pressure that makes the universe expand even more. That's the reason why the universe is expanding faster and faster all the time. But several scientists have suggested that, instead of a singularity, there might be something very different in the heart of the black hole – vacuum energy, which is one form of dark energy. Okay, but what is this dark energy? Everything on Earth and everything people have managed to see in space with the help of telescopes and other instruments is normal matter. It's made up of atoms and molecules and adds up to less than 5% of the universe. Around 27% of the universe is dark matter, and almost 3/4 of the universe is dark energy. Astronomers wouldn't even know the thing existed if, several decades ago, they hadn't found out that the expansion of the universe wasn't slowing down. Quite the opposite, it was accelerating. It meant there had to be some enigmatic force counteracting gravity, and it got dubbed dark energy. The European Space Agency's Planck satellite helped astronomers calculate how much dark energy the universe has to contain to explain the way its expansion is constantly speeding up. Scientists have also built models of how many giant stars formed and collapsed into black holes since the beginning of the universe. The conclusion is very exciting. The vacuum energy in these black holes is almost the same as the amount of dark energy that should exist in the universe. The scientists who conducted these experiments don't claim to have found the answer to the mystery of dark energy or to what we could see inside a black hole. But still, their theory is quite plausible. It can be tested with modern computer simulations and new data received from cutting-edge telescopes and other equipment. And now, let's speak a bit about dark matter. What it is and what it consists of. Actually, this is another thing that confuses scientists to no end. If dark energy is a force responsible for the expansion of the universe, dark matter is supposed to explain how objects work together. Potential candidates for dark matter vary from strange particles to super-dim objects. But even though astronomers can't grasp what exactly dark matter is, they know for sure what it isn't. It is dark, which means we can rule out visible stars and planets. It also can't be dark clouds of normal matter, otherwise scientists would be able to detect it. Dark matter is not antimatter. Astronomers don't see unique gamma rays that appear when antimatter comes in contact with matter. And neither is dark matter gigantic galaxy-sized black holes. There's one theory, though, and it's linked with a hypothetical concept of primordial black holes. Scientists have never got any real proof of their existence, but they think these black holes might be insanely old and quite tiny, by black hole standards, that is. Astronomers believe they could appear several milliseconds after the Big Bang. At that time, stars and galaxies weren't born yet. It means primordial black holes probably witnessed the entire history of the universe. By now, the smallest primordial black holes would have most likely evaporated away, but the bigger ones might still be scattered out there in space. Interestingly, these holes might be so small exactly because they popped up right after the Big Bang. The longer it took a black hole to appear, the larger it was. The mass difference between older, smaller, and younger, bigger black holes is incredible. Compare the mass 1,000 times greater than our Sun to that of a jelly bean. Yeah, you get it. So, there's this theory that primordial black holes could actually be dark matter. This idea remained unpopular for decades, but recently, scientists have realized there are many more black holes in the universe than they used to think, and it means the theory might actually work. And the vast and still hidden from us population of Big Bang black holes could not only make up, but be dark matter. After all, astronomers haven't discovered a single dark matter particle yet, even after decades of searching. At the same time, some scientists argue that dark matter can't be tons of multi-sized primordial black holes. They would collide far too often for this to work out. So, if you have a problem with all this stuff, just ask your nearest scientist, "Hey, what's the matter?" So, you're going on a journey to a black hole. Well, you'll need a lot of provisions, because the nearest black hole is 1,011 light-years away. This black pearl was found in the solar system called HR 6819. It was hidden in orbit with two other stars, which you can see with the human eye. Scientists have been studying this system since the 80s, but this winter it revealed its main secret. This particular black hole is considered relatively small, but despite this, its mass is 4 times bigger than our Sun, and it's 2,500 light-years closer to Earth than the next nearest black hole. But don't worry. For people, the distance of 1,000 light-years is unreachable. For example, if we were to make a model where the Earth's distance to the Sun was only 0.05 inches, you would have to travel about 4 miles to get to this black hole. But our galaxy, the Milky Way, is about 100,000 light-years wide. So the distance of 1,011 light-years doesn't seem that long in comparison. But before you jump inside this black giant, let me try to discourage you. A black hole is a place in space-time where nothing can leave its orbit. No particles, electromagnetic radiation, or even photons of light can escape from a black hole. So you should understand that a journey to such a dangerous object as a black hole is a one-way ticket. And the way black holes are born is incredible. When a star runs out of fuel, the star collapses under its own weight and becomes a black hole, like the supermassive black hole in the Messier 87 galaxy. Its mass is 7 billion times bigger than the Sun, and it was discovered by the Event Horizon Telescope in April 2019. Okay, good. I see you've already bought a ticket for a faster-than-light spaceship. Since there's no refunds, and you don't want to lose the money, it's time to get ready for the trip. Oh, feel free to leave your luggage at home. 3, 2, 1, off you go. You're leaving Earth's orbit, saying goodbye to the Moon, and don't forget to cheer up Pluto by saying it is big enough to be a planet. Then you pass the highway of dark space, and here's your stop, the black hole. Put on your suit, because you're going into outer space. The first thing you see is the event horizon. The gravitational field of a black hole bends the light around its edges, so the event horizon is like a croissant for the observer. Once you reach the event horizon, though, you won't be able to get back out. You may also notice that there's some kind of chaos in this ring. Some lights move in different directions. This happens because you get a mirror effect. But we still don't know what's inside the black hole, so you decide to send in a drone first. The gravity field of the black hole quickly draws in your metal buddy. As soon as he enters the event horizon, his body begins to change its shape. It becomes elongated like a strand of spaghetti. And the closer it gets to the center of the black hole, the longer it becomes. You also notice the drone has slowed its movement and now gradually approaches the black hole center. This is another effect of this space monster. The black hole's vast mass curves not only space but also time. If you hang one watch next to a black hole and another on the wall in your bedroom, you will see that in the first watch, the second hand has barely moved, while a whole day has passed on Earth. And the more massive the black hole, the stronger the effect of slowing time. Theoretically, if you have a spaceship that can overcome the gravity of a black hole, you can fly to it and wait for a few seconds. During this time, your friends on Earth would live a whole life. The flashlight on the head of your drone has turned red. This color change has happened for the same reason. The clocks that are deeper in a gravitational well tick slower when observed from outside. This also affects the photon's wavelength. We see red light because it has the longest wavelength of any color in the visible spectrum. All these things actually happen to the drone in a split second, but it seems slow to you because of the time warp. Alright, it's time to enter the black hole yourself. The final preparation is your suit that will protect you from Hawking radiation. This radiation is created by black holes due to quantum effects near the event horizon. Hawking radiation reduces the weight of the black hole. So if the black hole doesn't absorb more mass from nearby objects, it becomes smaller and then simply disappears. Oh yes, the black holes are also mortal. But Hawking radiation can turn you into ash, and you'd lose the chance to see the black hole from the inside. Okay, now let's do what you traveled 1,011 light-years to do. One big jump, and you are caught in the gravity field of the black hole. This is the point of no return. But your distance allows you to set a stable orbit so that you can spin around the black hole like the moon around the Earth. A little higher, and you'll be thrown into infinity. A little lower, and you will be dragged into the black hole. So, theoretically, planets could exist at this distance, and even inhabited if there were the necessary conditions. A couple of minutes later, and you are approaching the event horizon. Oh, look down. Your body is so long. You are now spaghetti yourself. Look around you. The stars are turning blue. This is called gravitational blue shift. As you fall into a black hole, its gravitational field pulls the photons of light down, giving them energy. Their wavelengths are getting shorter, so the red photons change into blue and everything starts to look blue. Now you are right outside the event horizon, and the only thing you can see is a round blue beam of light above you. But soon you will stop seeing even that. So you've survived the strong gravitational field of a black hole, and the Hawking radiation didn't burn you to ash. You are now in the heart of the most mysterious object in the universe. You have front row seats, but the view is not that impressive. This is the darkest place you've ever been to. Even the usual laws of physics just stop working here. Theoretically, time goes by so slowly here that your home planet could no longer exist, and a new black hole could appear in place of our sun. But you will live exactly as long as there's enough oxygen in your suit. But what if this cosmic object is actually a wormhole that leads to another place in the universe? This is a popular theory, but scientists still can't confirm it. But if it is true, then after a while, you'll see a blue light again. Now you'll experience the same fall, only in reverse. Once you leave the singularity, which means the black hole's heart, you will be in the event horizon. The light from the stars gradually changes from blue to red. You can feel the shaking and warmth from the Hawking radiation. But then you're thrown into outer space, perhaps in some faraway galaxy. No one knows what will happen next. Are you in contact with an unknown life form? Or will the conditions there be intolerable for a human being? Or maybe you will not go to another place in space, but to a parallel universe. This theory also exists. According to it, black holes are portals to other dimensions. Simply put, there are endless copies of our universe. Every time you were faced with a choice, your twin from another universe chose something else. But let's leave that to fantastic movies. Right now, the journey into a black hole is merely impossible for humanity. We can't even reach the nearest one. But one day, we will learn more about these space objects' nature. And maybe this knowledge will push humanity forward and make us a multi-galactic civilization.
Here's something cool that scientists have discovered recently: Schrodinger's black holes. Yep, the scariest objects in our universe turned out to be even more terrifying. Now, we know that they can also exist in many states at once. But what does it mean? Let's find out. Black holes are mysterious titans of our universe. Sometimes it feels like the more we learn about them, the less we know. We discovered them quite recently, in the 20th century, and since then, we've been finding various black holes all over the universe. Their sizes range from the size of a small town to horrifyingly unimaginable. But their most important feature is probably their huge mass. And that's where a recent study comes to play. Scientists have discovered that black holes have very unusual quantum properties. They found out that each black hole can be both large and small, light and heavy, no longer living and alive. Well, maybe except for the last part. Let's hope that there aren't actually any living black holes. That would be great. But the main point of the discovery is that each black hole can be in all possible states at the same time. It sounds weird, doesn't it? What is it actually supposed to mean? Well, the ability to be everything at the same time isn't a new concept in science. This is what physicists call a superposition, or, to put it simply, a state of uncertainty. Quantum physicists discovered this first in tiny quantum particles. They noticed a very strange thing. As long as we don't observe a particle, it literally exists in all states at the same time. And only when we start interacting with it, for example, looking at it, measuring it, or just doing something, only then does the particle decide what state it should be in. Here's an example of this. Imagine that you have a ball in a box. You don't know what it looks like, and the thing is, as long as it stays in the box, the ball is all colors at the same time. Only when you take it out of the box does it finally choose one color. All this happens instantly, so you don't notice it. For you, the ball has always been blue. Sounds pretty scary, right?
What?
And it raises a lot of questions. For example, how do these particles understand that we're observing them? How do they decide which state to be in? And what does our world really look like if we only see what is shown to us? Of course, this discovery caused a huge stir in the scientific community. No wonder, it does sound a bit unusual. That's what physicist Erwin Schrödinger also thought at the beginning of the 20th century. The ideas of quantum theories seemed delusional to him. That's why he decided to challenge them. He conducted a famous experiment. You've probably heard about it, even if you don't know anything about science at all. Yep, the infamous experiment with Schrödinger's cat. So, what was the point of the experiment? First of all, we have a box and a cat. In the box, there's a container with toxic gas and a special mechanism. Every hour, there's a 50% chance that this mechanism will either open the gas container or not. If it happens, the poisonous gas will be released and the poor cat won't make it. If this doesn't happen, the cat will remain alive and well. Don't worry, this was a purely hypothetical experiment. No cats were harmed in the process. But let's imagine that we did lock a cat in a box and waited for an hour. It's time to check the result. And here's where we get close to the most interesting part. How do you think this situation would end in our regular world? Well, probably within an hour, the container would either open or not, and that would be the moment sealing the cat's fate. After that, we just need to open the lid to find out the answer. But in quantum physics, everything is much stranger. According to it, until we open the box, the cat inside would be both alive and not alive at the same time. In other words, the universe itself doesn't know what to do with this cat. As if the poor animal is on the verge of two worlds inside the box. And when you open the lid, the universe will select a random result of the experiment. So why do we do all this to a poor kitty? Well, initially, Erwin Schrödinger wanted to show how stupid it all sounded. But then, he accidentally proved that quantum physicists were right. The situation turned out to be pretty funny. It went like this. Ha ha ha, these quantum physicists have no idea what they're talking about. According to their logic, the cat in my box should be both alive and not alive at the same time. Wait, hold on. Uh-oh, they're right. Schrödinger received the Nobel Prize in 1933, even though it wasn't for this discovery. And in 2022, 3 more scientists received the Nobel Prize for another discovery in this field.
Thank you.
These scientists were Alan Aspect, John F. Clauser, and Anton Zeilinger. They got it for their experiments that involved entangled quantum states. What does all this tell us? Guess now we'll have to look for explanations in some kind of quantum mechanical magic. Unfortunately, humanity isn't developed well enough to test any of these theories, yet. But we have many cool assumptions. For example, the theory of parallel universes is one of the attempts to explain this phenomenon. Remember that ball in the box? Basically, according to the theory of the multiverse, there's an infinite number of different realities. So, if you don't know what the ball looks like, it kind of exists in this interdimensional, uncertain state. But when you open the box and look at the ball, you get transported to a random reality. For example, to the one where it's blue. It sounds pretty incredible, but still exciting. Alright, but why do we need all this info now? Why is it connected to the recent discovery? You see, scientists thought, if teeny tiny particles in our universe behave like this, then what about some giant space objects? And so, they decided to direct their devices not into the microcosm, but into distant space. American and Israeli theoretical physicist Jacob Bekenstein was the first to suggest that black holes may have the same weird properties, but this theory had to be tested. The research itself was aimed at finding a connection between quantum particles and black holes. The researchers created a computer structure in which they placed a simulated quantum particle directly outside a giant simulated black hole. And in the end, this analysis showed that, yep, black holes could also exist in several states at once. For example, they can be incredibly massive and at the same time have no mass at all. And each of these mysterious space gates can have several masses at the same time. The modeling showed that these superimposed masses were, in fact, in certain determined bands or ratios, as predicted by Bekenstein, said the physicist Magdalena Zeik, referring to the study. It's not really clear yet what it all means, and this discovery alone hasn't brought us much closer to understanding how our universe works, or what happens inside black holes. We have realized only one thing. Everything around us is much more complicated and more fantastic than we think. Who knows? Maybe black holes are portals between these parallel universes. At this stage, it's impossible to disprove this. In other words, the universe has once again shown us that it is stranger and more mysterious and fascinating than we could imagine. Let's hope that in the future, we'll be able to understand at least a bit of what's going on in it.
We all know about black holes, but what about their mysterious twin siblings, white holes? Have you ever even heard about these guys? Do they even exist? And the most important question of them all, are these two actually a big interdimensional portal? Let's find out. A black hole is a creepy space object with an incredibly strong attractive force. Its gravitation is so great that even light cannot escape from it. That's why it seems black to us. They appear when stars at least 3 times bigger than our sun completely burn out. Turning old, such a star begins to shed layers of gas and decrease in size. Its core shrinks and shrinks until it turns into a small ball with huge pressure inside. And when it can't withstand this pressure anymore, it goes boom, collapsing on itself and becoming a black hole. And yeah, we still have a lot to learn about these guys, but at least we have some rough idea about them. But what about white holes? Why do we hear about them so rarely? And why don't we know anything about them? White holes are theoretical space objects that are basically the opposites of black holes. If black holes eat everything they see, then white holes, on the contrary, don't let anything enter them. By the way, white holes is just a name. To us, they wouldn't actually look white. Imagine traveling in a spaceship. Suddenly, you see something that looks like a typical black hole. It's surrounded by a bright, rotating, massive ring of space dust and gas. But if you continue to watch, you'll see something unusual. This hole will spit out some matter from its center. Something like this is impossible with black holes. Only at this moment will you realize that this is a white hole, because visually, they have no difference. Both of these space phenomena have the so-called event horizon, which is something like a boundary. For a black hole, this boundary becomes the point of no return. If you cross it, there's no way back for you. But for a white hole, it's more like an invisible wall you can't get through. It's like an exclusive club. for no one. Here's something interesting to think about. Once, a white hole got a huge amount of material from somewhere, somehow. But then, it stopped absorbing this material and started spitting it out. So that means that it spits out remnants of the past. But what exactly is this past? Can a white hole spit out something that once existed and has long disappeared? Can these things somehow affect our world? This thought may be a little worrying, but you can relax. The thing is, we haven't discovered even a single white hole yet. It may be because we have very little actual knowledge about space. In the 20th century, Albert Einstein and his general theory of relativity hit physics like a tsunami. He discovered something incredible, that gravity, as an invisible almighty force, is able to bend space and time. This discovery was a real breakthrough. That's when scientists first suggested the existence of black holes. But it took them more than 40 years to understand these space objects, or even prove their existence. Only recently did we receive the first photo of a black hole located in the center of the galaxy M87. You might remember that one. Many people laughed at the fact that it was too blurry, but we really should give scientists more credit. This photo was obtained through international collaboration of space stations and 8 ground-based telescopes. So basically, we needed a huge amount of effort and resources to get even small proof of the existence of black holes. No wonder we still haven't discovered their twins. But on the other hand, many scientists now think that white holes may not even exist. For a long time, they were a logical conclusion of the theory of relativity. If black holes exist, why shouldn't white holes appear in the universe? But recently, scientists have begun to question if white holes are even possible. We know how black holes are born, but for a white hole to appear, this whole process needs to be reversed, which doesn't make a lot of sense. We can take an egg and turn it into an omelet, but how do we turn an omelet back into a whole egg? That's not only about food. At first, everything in the universe has some clear, definite shape, and then, over time, it becomes more and more chaotic. This is one of the universe's statistical laws. Moreover, it seems like white holes wouldn't be able to exist for a long time. They would throw a lot of their mass and material into space. All this would gather and gather around them, until, eventually, a white hole would collapse and form another black hole. What a weird cycle. But this is what this process looks like if you use common sense. But we all know that the universe is way too cool for our small, simple brains. There are so many things in it that don't make any sense, but they still exist. Some physicists are trying to bring white holes back from scientific oblivion. Their main argument begins with the question, what happens with things that enter a black hole? They can't just disappear into nowhere. According to physics, no matter in the universe can simply turn into nothing. It never disappears. It just changes. So what happens inside a black hole? What happens to a black hole itself when its lifespan expires? And how is a white hole born? As you've probably guessed, these questions may all have one answer. The two holes must be interconnected, and they may even be some sort of portal. For this to be true, we need to violate the equations of general relativity. And we know that Einstein's theory has been considered inviolable for years. But here's a fun fact. We did finally challenge it in 2022. 3 scientists got the Nobel Prize for proving that Einstein wasn't right about many things, and the universe is way more complicated than we thought. In other words, white holes can really exist. They may be kind of crazy and incomprehensible to us, but their existence is still possible. If they did, how would they work? Well, we have a few ideas. For example, some suggest that a white hole could be a child of a black hole. Over time, a black hole could grow old and become very small. Then, the processes taking place in it would cease to obey common sense. Pure quantum randomness would come into play. Yada yada, particles create some madness and chaos, and boom! A black hole turns into a white hole. Such a white hole would be the size of a tiny particle and weigh about as much as a strand of human hair. It wouldn't have the incredible gravitational mass of its ancestor, but it would have its insides. In other words, this white hole would store everything that the black hole swallowed in its previous life, and sooner or later, it would start spitting this information out. If this theory is true, then one day, white holes may begin to dominate our entire universe. This could happen when all the stars burn out and all the black holes dry up. But that's in the most distant future you can imagine. We're talking about trillions of years in the future here. The universe may not even survive for so long. There's also another option. Maybe our entire universe is the creation of a white hole. Some physicists say that the Big Bang looks suspiciously like the potential behavior of a white hole. Both of them are very similar mathematically, and who knows, maybe they're right. In any case, there are tons of things in our universe we have no idea about, and maybe one day we'll discover the secret of these twins. Let's just hope that they'll turn out to be some cool interdimensional portals.
We're traveling 1,000 light years from our planet to an unfamiliar system. Here, there are two bright stars orbiting close to each other. But there is one small but very massive thing here as well, a black hole. These objects are mysterious and dangerous. They're capable of swallowing our entire world in 1 second without even noticing it. Even more, they can tear apart a huge star like our Sun. And it's these giants that usually lie at the centers of galaxies. They're so heavy that their gravity holds countless stars, planets, and stardust around them. They can weigh millions or even billions of times more than the Sun. And now, you're back on the ground at a rocket launch pad on Earth. All you can think about is holding your breath and jumping into the heart of that black pearl. But you don't have to hold your breath because you'll be in a spacesuit, and the oxygen is included free of charge. Besides, you're not likely to ever make it to the black hole. A trip that far with the technology we have now would take tens of thousands of years. Back to your garage where you stashed your hyper rocket, which will take you to the black hole in seconds. And you're next to two stars in a black hole. First thing you notice is that the black holes aren't black. Its gravitational force pulls in not only objects, but even light itself. This makes the hole invisible. You can only see a bright ring around it. That's called the event horizon. It consists of twisted light, hot dust, plasma, and pieces of asteroids that are also trapped there. So the event horizon is the first obstacle to overcome. Okay, you put on your jetpack, open your rocket's door, and jump towards the black hole. The force of gravity begins to pull you quickly toward it. The spacesuit protects you from the enormous temperatures and levels of radiation on the event horizon. Conventional protective gear would hardly help you, so you thank your dad for stashing this super powerful protective suit in your garage as well. You begin to feel like your body's stretching unpleasantly. The problem is that gravity increases with every inch closer to the center of the black hole, and it's much stronger at your head than at your feet. Your body starts to stretch like spaghetti. That's why it's called spaghettification. No suit can protect you from that, and there isn't a single spaceship that can withstand that kind of strain. Well, this was a short video. Okay, let's rewind to the moment before the jump. You realize that to get to the heart of the black hole and survive, you don't need improved equipment, but another black hole. And it's the size and weight of it that matters here. Theoretically, you can survive falling into a supermassive black hole. It's all about the width of the black hole's event horizon. When a hole is small, about the weight of our Sun, the event horizon is small too. And then its edge is remarkably close to the center of the abnormal gravitational force, which would make you spaghettified quickly and brutally. But if the event horizon is wide, it's farther from the center of the gravitational force. Then the difference of gravity pressing on your head and feet will be non-existent. So if you have enough air in your spacesuit, you can survive such a journey. So you must pick a supermassive black hole. Let's see. One at the center of the Milky Way? No, there's too much hot plasma and debris around it. You need a completely isolated black hole for a jump like this. Somewhere in dark space where it hasn't had time to gather the debris of neighboring worlds around it. You quickly open your space map and find such a black hole. One faster than light trip, and you've arrived. There it is! A huge dark nothing. There's only distorted light from distant stars and galaxies on its event horizon. To test your theory, you throw a mannequin into it. It approaches the black hole and then slows to a standstill. But it's just an illusion. The black hole is so heavy it can warp both space and time. So, to the observer, the dummy is frozen in the event horizon, but it has long since entered its heart. The dummy didn't get spaghettified like you did when you fell into a small black hole, so now you're confidently jumping after it. Remember that even if you feel fine, it's still a one-way trip. Once in the black hole's field of attraction, nothing can escape its embrace, no matter how powerful a rocket you have or how hard you flap your arm. You're now at the edge of the accretion disk. Every second here equals weeks or months on Earth. You're traveling through time. Our home planet may already have flying cars and skyscrapers several miles tall all over the place. But for you, it's only a couple of minutes. Whoa! All the light you see from the stars has turned red. That too is because of gravity. The light we see is waves, but the black hole stretches them out. The short wavelengths of blue become long and red. Great! You've passed the event horizon and are now heading into black nothingness. You look up and see a thin ray of light. The last thing you see, in fact. After that, there's just black void. No one knows what happens next. Some theories say black holes can be portals to another dimension, or to another place in the universe. By jumping into a black hole in our galaxy, you can jump hundreds of thousands of light years away from our home. In that case, you will experience your fall in reverse. First, you see a small but expanding beam of light. Then, red starlight returns to blue. And before you know it, you're back on the event horizon. And soon after, you're free of the black hole's pool. But scientists still can't confirm this theory. Okay, that's too grim. So just this time, we'll bring you back to Earth in the company of your friends. They praise you for your accomplishment of surviving the center of a black hole. Now you're the heart of the company, and no black hole can scare you. But even the biggest black hole in space isn't as scary as you might think. They have a lifespan. That radiation I mentioned takes energy from the black hole. If it doesn't have food around it, the hole starts to deflate like a balloon, and eventually there's nothing left. Another fear around black holes is that we can create one at home. Indeed, inside the Large Hadron Collider, scientists conduct experiments with small particles colliding at high speed. There are huge bursts of energy, and some scientists believe this energy is enough to create a microscopic black hole. It will begin to absorb its surroundings and grow. First, some small objects in the room where it was created, then the entire lab. The hole continues to grow and is already consuming our whole planet. It changes the balance of power in our solar system and absorbs the planets one by one. When those are finished, it's time for dessert, the sun. The light upper layers of plasma are stretched into long spaghetti and pulled toward the black hole. Then, layer by layer, our star collapses into the dark abyss. When the sun is half absorbed, the black hole shoots a beam of energy and light outwards and continues to consume the sun. In mere moments, there's nothing left of our solar system. That's how some people describe the end of the world. But even if we do manage to create a microscopic black hole, we'll be safe. It'll be too small to absorb big objects, and it will only feed on small atomic particles. Black holes emit energy as well as consume it, so our little one won't have time to grow. It'll lose more than it finds in a fraction of a second. So what you'll see is a momentary flash and then nothing. Although creating a stable and controlled black hole may even be useful. They emit enormous amounts of energy that we can use. A black hole the mass of Mount Everest could power all of humanity. Of course, black holes are still dangerous, but we can watch them and study our universe. If we stay far enough away, of course. So, you decide to put a padlock on that garage door. For now. Dark, ever-hungry monsters live all across the universe. They're born when massive stars blast into space. Black holes, as heavy as Earth, are just as large as a ping-pong ball. They don't have a surface, but their gravity is so strong even light can't escape it. Black holes don't have physical boundaries like a membrane either. The event horizon, which is closest to a typical boundary, is a threshold which, after passing, you can't get out. For a star, running into a black hole normally ends in a spectacular light show and its destruction. Just one star that astronomers know of managed to survive an encounter with a black hole as heavy as 400,000 suns. It happened in a galaxy about 250 million light-years away from Earth. Astronomers with really powerful equipment noticed bursts of X-rays that raged in space every 9 hours. They thought they must be Mayday signals from a star trapped by a cosmic abyss. The star was an average red giant when it met its new friend for the first time. When they got too close to each other, the hungry space monster couldn't resist the temptation and snacked on its guest. When it was done with the star's outer hydrogen layers, all that was left was the star's core. Eventually, the poor thing turned into a white dwarf. But for some reason, the giant space monster couldn't finish the meal and trapped it in its orbit for later instead. Ever since, the now white dwarf has been traveling in 9-hour laps. It stays far enough from the hole so it won't fall in or get swallowed. Its journey isn't going super smoothly. Because of gravity, the orbital path is constantly rotating. After 2 days, it resembles a spirograph pattern. As the black hole keeps snacking on it, the star keeps losing its mass and growing in size. Its own orbit is becoming more and more circular. Scientists believe one day it will be able to spiral away from its mean friend and turn into a planet the size of Jupiter in 1 trillion years. That's 70 times longer than the universe has existed so far, so it might not ever happen. The Milky Way alone has hundreds of millions of black holes, and there are way more beyond it. They might feed on other stars and release them in other galaxies. The telescopes that exist now might not be strong enough to spot them. Most galaxies, including our Milky Way, have supermassive black holes at the center. They can be billions of times heavier than the Sun. Others of their kind are only 3 times the mass of the Sun. The nearest black hole to the Earth was spotted 1,000 light-years away, just around the corner in galactic terms. It's in a star system you can see with an unaided eye. Scientists found it when they noticed a star behaving weirdly. It was a giant rotating like crazy. They guessed it must have a powerful gravitational companion. The hungriest black hole astronomers have spotted so far weighs as much as 34 billion suns and is about 6 times bigger than the one at the center of the Milky Way. It eats the equivalent of 1 sun every day. Sometimes black holes even devour others of their kind that happen to be too close to them. Before you get on a spaceship to escape to some safe, no black hole galaxy, here's some good news. Even though they're supermassive, they don't have a radius large enough to destroy Earth. And even the hungriest of them are safe to watch from a distance. No black hole should come closer to our planet than the Sun for as long as the universe has existed, multiplied by 10 billion times. In the unlikely case one of these scary things passes by Neptune, it could affect the Earth's orbit. That would be no good. In theory, anything can turn into a black hole. The only difference between it and the Sun is the material their centers are made of. It's incredibly dense in those huge space monsters. In reality, there's just one known way to make a black hole. It has to be the gravitational collapse of a supermassive star, 20 to 30 times the mass of the Sun. So, the Sun will never ever become a black hole. If it happened, though, and the former star retained its mass, it would still have the same gravitational power. Earth would still keep going around it and wouldn't get pulled in. Its orbit would also remain as it is. The only huge problem would be the lack of sunlight. In reality, the Sun isn't massive enough for such a transformation and will eventually become a white dwarf. A black hole won't ever eat an entire galaxy for lunch. There are about 400 billion stars inside the Milky Way. Just around 0.1% of all the stars that will ever form will end up becoming black holes. The ever-hungry supermassive monster, located right in the middle of a galaxy, has an impressive gravitational reach. But even that wouldn't be enough. It has already eaten most of the stars that were close to it. It already weighs like a few million suns, so it can't grow much larger even if it keeps snacking on sun-like stars. Galaxies will keep bumping into each other, and black holes will keep growing and merging. But because the universe is already huge and keeps expanding, these collisions and mergers won't go on forever. Black holes will travel this huge space like rogue stars. They won't even be able to eat the dark matter on the outskirts of galaxies. Eventually, all the black holes will perish, but that would be a long, long time from now. If you ever become a space explorer and travel far enough to meet a black hole and fall into one, your life won't instantly end. Instead, things will be way more complicated. The way you perceive space and time will change, and your reality will split in two. In one of them, you'd cease existing. In the other, you'd live and enter the hole unharmed. When you go deeper inside the hole, you'll notice space becoming curvier and curvier. At the center of the hole, it's infinitely curved. It's called singularity. Laws of physics based on the ideas of space and time don't have power here. In a large enough hole, millions of times more massive than the Sun, things would go perfectly smoothly for you. And you just keep free-falling, feeling no gravity. You could just keep falling and falling in total emptiness until you reach singularity. You'd have no chance to move in the opposite direction. In there, space and time switch roles. Time is constantly pulling you forward on Earth, but figuratively, and it would be doing that quite physically inside the hole. In a smaller hole, the force of gravity would be stronger at your feet than your head. That's why you would go through spaghettification. This is how scientists call the process when you compress horizontally and stretch vertically like spaghetti because of crazy gravity of the black hole. Speaking of spaghetti, how are black holes like an Italian dinner? Because once you go pasta the event horizon, you get spaghettified, and since you're all by yourself, you'd be feeling cannelloni right now. Wow, now I'm hungry. Meanwhile, if you had a fellow space traveler who, for some reason, didn't end up in the black hole, it would look all different to them. They'd see you stretch and grow, like through a huge magnifying glass. The closer you get to the edge of the hole, the more it would seem like you're moving in slow motion. Then you'd freeze, and the flames would surround you. You'd be in two places at the same time, living different destinies, but there would still be just one copy of you. This is how black holes teach us nothing is real. Reality can be different to different people. Some scientists believe that we're all living inside a huge black hole. Everything in the universe started with the Big Bang. But there's a theory saying there was also something before that. It was a super dense seed that had all the mass and energy of the universe concentrated in it, about as heavy as 1 billion suns. It was 1 trillion times smaller than any particle humans can observe. This seed could be born inside a black hole. If you believe there's more than one universe, black holes could also serve as doors between those universes. It could be like a root that two trees share. You can't see a black hole directly because it doesn't give off any light. Scientists used to be able to only spot them by what they were doing to their surroundings. When over 200 scientists around the world worked together, they managed to take the first pictures of that space oddity. The equipment they used, added together, would be the power of a telescope the size of Earth. Now, did you know that there's an astronomical object in which space and time actually swap places? How does that work? And what exactly does swapping space and time mean? Well, let's figure it out. Imagine that you're on a spacecraft. The vehicle can only move straight. Your path leads to some inevitable point, and you have no idea what lies ahead. You can only hope that it won't be too bad. Meanwhile, everything around you is complete madness. A chaotic collage of many historical events. What do you see? Ancient humans and dinosaurs? The birth of the universe? Future? Who knows? That's what the universe would look like if we swapped time and space. And theoretically, this is what you would see if you fell into a black hole and somehow were able to survive. But how is something like this even possible? First of all, let's discuss time and space. Imagine drawing a light bulb on a sheet of paper. Then grab one more sheet and draw how it lit up. Right now, it's just a small circle of light. Another sheet, the circle of light is growing. It gets bigger and bigger in size until finally it turns into a giant circle. In real life, the bulb lights up in the blink of an eye. That's because the speed of light is the fastest in the universe. But here, on our drawings, we capture the propagation of light frame by frame. We see how over time the light has grown from a small dot to a large circle. But if you connect these circles, doesn't it remind you of some shape? For example, a cone? Yes, exactly. This is called a light cone, and time is the central axis of this cone. Why? Because light turns from a small dot into a large circle over time. To remember it, let's draw a time vector, an arrow inside the cone. It goes from the past to the future. Meanwhile, the circles are space. In space, we can move however we want, in any direction. We can move up or down, in zigzags, and so on. But no matter what zigzags we draw along the timeline, we're always moving forward. We can't turn back in time, and we can't stop it. This helps us define time and space. Time is the direction in which the light cone is oriented. This is the direction where all our paths lead, and where our future inevitably lies. And space is the whole variety of directions perpendicular to the timeline. This is a straightforward graph. If it could be applied to the entire universe, then time would flow the same everywhere. However, if you've watched at least some popular sci-fi movies, you know that this isn't the case. In reality, time can be crazy. For example, if you're chilling near a black hole, what will be 2 hours for you may turn out to be 20 years for your friend on Earth. But why? Well, take a deep breath. Now, gravity comes into play. Oh, I know about gravity. It's that thing that helps me to stand on the ground, you may think. But it's much, much more complicated than that. Gravity is one of the basic physical forces in our world, and it's incredibly powerful. In fact, she's such a girl boss that she can distort space and time. She can literally influence the speed of time like an almighty wizard. How? Well, let's take something slightly bigger than a light bulb. For example, a supernova. Somewhere in the universe, a star has just made a boom. How do we know about it? Well, nothing in the universe, no sound, no radio waves, nothing, travels faster than light. So we'll know about the birth of a supernova only when we see it. And this will happen only when its light cone grows enough and reaches our planet. So the light cone grows and grows. So far, everything is fine. And finally, it reaches our planet. But there's a catch. You see, our planet is very massive, and it has pretty strong gravity. What happens then? Gravity changes the direction of the light cone. It begins to attract the cone to the center of our planet, and with it, it also attracts our arrow of time. That means it slows the time down, and the closer the light cone is to us, the more the arrow bends and the slower time goes. What does it mean? Well, for example, the fact that the watch on your ankle will lag behind the watch on your wrist, that your head is aging faster than your legs, and that astronauts in Earth's orbit age a little slower than people on Earth. This is what scientists call general relativity. Right. But how does this relate to our topic? How can we understand what will happen if we swap space and time? Don't worry, we're almost there. Now, imagine a cosmic body with incredibly strong gravity. It bends time and space so much that it feels like they swap. This is a black hole. A black hole attracts absolutely everything to its center. No stars, planets, no light can escape from there. Let's say our light cone is approaching it. First, as usual, time begins to bend toward the center of the black hole, attracted by its gravity. But the gravity is very strong, so it bends more and more, and time goes slower and slower the closer you're to the center. In the end, the light cone crosses the boundary of the black hole, the so-called event horizon. At this point, it gets so distorted that now it's literally pointing downwards. We can say that time has changed its direction. Time is pointing downwards. What kind of nonsense is that, you may ask? It'll be easier to explain in a real example. Imagine you're a crazy astronaut who decided to jump into a black hole, and there's an observer in the spaceship who watches you doing this for some reason. At first, for you, nothing changes. You look at your watch, you see that 5 minutes have passed, and everything's okay. But for the observer, first of all, you'll fall for a very long time. The observer has been sitting there for 50 years, and you're still falling, all because your time has slowed down. Secondly, since space is also distorted near the black hole, the observer will see how you'll begin to stretch like spaghetti. This is a scientific term, by the way. It's called spaghettification. And then you finally cross the event horizon. The observer doesn't see you anymore. Light cannot escape from a black hole, so your image won't reach the observer even if you're still inside. And what about you? What if you somehow survived? Remember, the time arrow is pointing to the center of the black hole. What does it mean? It means that now, the center of the black hole is your future. It isn't a place, it's a fate that you can't change. And wherever you came from, as well as the rest of the universe, no longer exists for you. Because now, it's not a place, but an event from the past. And since you can't turn back time, you'll never be able to come back. But what is around you? Complete chaos. The rays of light now move in all directions, forward, backward, and so on. The rays depicting the events of the past, the future, the present, all this is moving around you. In reality, space and time didn't swap places, but it feels like they did. Because in space, you can now only move forward, as if along a straight line. And time, reflected in the light rays, surrounds you everywhere and moves in all possible directions. And here we go back to the beginning. This horrifying example helps us imagine what it would feel like if time and space got reversed. Of course, all this is just theories and guesses. The very idea that we're moving in some one direction, the one we haven't chosen, and there's complete time chaos around, sounds quite frightening. And yet, it would be a very interesting experience. Sounds dangerous. Why don't you go first? Oh, fasten your seatbelts. We're setting course for the most bizarre places in our universe, and you'll see the most mysterious phenomena few people have ever seen before. Recently, astronomers have discovered that the supermassive black hole at the center of our home Milky Way galaxy might be leaking. Why is it a significant change? Because it might mean that this black hole, called Sagittarius A star, whose mass is 4.1 million times the mass of our Sun, isn't a sleeping giant as previously thought. It might still be active. And the leakage, recorded by scientists, may be the hole hiccuping while swallowing clouds of gas. Hey, I've been known to do that from time to time. During the research, the team of astronomers used the Hubble Space Telescope. It helped them spot a jet that looked like a blowtorch. It was pushing into clouds of hydrogen at the center of our galaxy. The jet seemed to spew gas like a hose directed into a pile of sand. This often occurs around other active black holes surrounded by the material drawn to them by their immense gravitational pull. Some of this material gets pulled into the black hole, but a small part of it gets swept outward by powerful magnetic fields. The research suggests that when a giant gas cloud gets too close to our supermassive black hole, it gets swallowed, and then the hole belches small jets of matter. Fermi bubbles might be the result of the belches that occurred around 2 to 4 million years ago. But recently, scientists have found another giant glowing bubble of hot gas. It aligned with the jet stretching for 35 light-years or more from the supermassive black hole. Astronomers suspect that the jet could have plowed into this bubble of gas and inflated it. Now, let's visit some other breathtaking places in our universe. But be careful, some of them are extremely dangerous. Like this rotating neutron star called the Black Widow pulsar. Just like its spider namesake, it's munching on its partner, a lightweight brown dwarf star. The more material this pulsar consumes, the more slowly it spins. The energy the neutron star is losing in the process causes the companion star to dwindle. If it does exist, nuclear pasta is the strongest material in the entire universe. Formed from the leftovers of extinguished stars, this substance gets squeezed into spaghetti-like tangles of material. It can break, but only if you apply 10 billion times the pressure needed to shatter steel. How about visiting a planet where it rains glass? Nah, I'd rather not. You see, this bright blue exoplanet looks peaceful and slightly familiar. Don't you think it slightly resembles Earth? But this pretty appearance hides the planet's terrifying nature. The winds blow at 5,400 miles per hour on its surface. That's 7 times the speed of sound. But that's not the worst. It rains glass sideways in this scorching hot alien world. Solar tsunamis are a solar phenomenon dubbed Terminator events. These tsunamis take place at the sun's equator. Disastrous magnetic field collisions seem to cause ginormous twin tsunamis of plasma. These tsunamis tear across the star's surface, moving at a speed of 1,000 feet per second. They can last for weeks at a time and happen every decade or so. Now look at this space body. Its nickname is Electric Hyperion. This Saturn's moon is one of the most bizarre-looking moons in the solar system, but its appearance isn't the strangest thing about it. This pumice stone-like rock, pockmarked with countless craters, is also charged with static electricity, and it's flowing out into space. Look at this, a rogue planet with auroras. Lost in space and drifting through galaxies, rogue planets were once flung away from their parent stars. But one of them, 200 light-years away from Earth, is different from the rest. It's a planet-sized object with a magnetic field 200 times stronger than that of Jupiter. This field is so powerful that it generates flashing auroras in the planet's atmosphere. Be sure to stay away from black holes. Do I really need to warn you? Yep, they're some of the most perilous objects in the universe. But how about mini black holes? Unlike their massive siblings, hypothetical mini black holes could be really tiny, not bigger than an atom. Even so, just one minuscule thing would have the mass of 1,000 sedans. One theory claims that tons of micro black holes could have been created right after the Big Bang and the beginning of the universe. Some scientists even go as far as to say that a couple of mini black holes pass through our planet every day. Ooh, I'll bet you like our next stop, a burning ice planet. Faraway Neptune-sized exoplanet Gliese 436b is a paradox. It's made of scorching hot ice. The planet completes one full orbit around the red dwarf Gliese 436 in just 2 days. It means it's traveling remarkably close to its parent star. That might be the reason the planet's temperatures rarely drop below 800 degrees Fahrenheit. But the strangest thing? The planet hosts huge volumes of water ice known as Ice X, which remains solid despite blistering temperatures. Now, if you love jewelry, this next world is for you, a diamond planet. About 4,000 light-years away from Earth, there's a planet that seems to be one enormous diamond. The planet is denser than any other discovered so far and consists mostly of carbon. It's so dense that astronomers think this carbon might be crystalline. This in turn might mean that at least some part of the planet is diamond. Moons orbiting other moons might exist, or they might not. Astronomers haven't agreed on this one yet. Planets orbit stars, and moons orbit planets. But then, why can't there be moons, also known as submoons, moonettes, and moons? It actually sounds like one of those flowery Hawaiian dresses, moo-moos. But alas, no. Researchers claim that moons could exist, but the host moon has to be massive enough, the moon small enough, and there must be a wide gulf between these moons and the host planet. Now, I'll take you to the living fossil galaxy. DG-SAT-1 is as big as the Milky Way, but it's nearly invisible because its stars are spread out incredibly thinly. But what makes the galaxy unique is that it's sitting all alone, unlike other galaxies of this kind. Those are usually found in clusters. It can mean that DG-SAT-1 was formed in a different era, probably a mere 1 billion years after the Big Bang. If it's true, this galaxy is a real living fossil. Now, you won't be able to see the next space phenomenon, all because people can't see infrared light. And the phenomenon I'm talking about is an infrared stream from space. Ooh. Neutron stars are ultra-dense collapsed cores of giant stars. They usually emit X-rays or radio waves. But in 2018, astronomers discovered a weird stream of infrared light. It seemed to be coming from a neutron star 800 light-years away from our planet. This signal was probably generated by a disk of dust surrounding the star, but this theory hasn't been proven yet. Behind the orbit of Neptune lies the mysterious Kuiper Belt, filled with massive icy objects. The most curious thing about this space formation, though, is that scientists fail to explain the pattern of its movement. The only explanation they have is that Neptune might be hiding from our sight a ginormous planet. This hypothetical planet has already got the name Planet 9, and all we have to do is wait until its existence is confirmed, or not. Let's visit our star, but we need to be careful not to come too close, because the Sun's atmosphere is hotter than the surface of the star. While on the surface, the temperature reaches 10,000 degrees Fahrenheit, the upper atmosphere heats up to millions of degrees. Scientists suspect that explosive bursts of heat from the Sun may have something to do with this unique phenomenon. Now, this space object is also worth visiting. Haumea, a dwarf planet orbiting in the Kuiper Belt, has a bizarre elongated shape and 2 moons. The day on this planet lasts 4 hours, making it the fastest spinning big object in our solar system. But the most mysterious thing about Haumea is that the planet has a thin 40-mile wide ring